This is the first section in the module Production Separator Principles. Section 1 introduces you to the basics of separators. To begin with, we will take a look at the principles of fluid separation. Then we will examine a typical production separator and its components. Finally, we will follow the flow of fluids through a separator. To some, it's not a particularly exciting vessel, but production separators provide an essential service in the oil field. Their efficient operation is critical to the separation process. But let's back up for just a minute. Remember I said the well fluids are made up of oil, water, gas, and sand all mixed together? The production separator breaks up the emulsion into various parts. Now, it isn't done with magic, but with some very basic principles and a force we're all familiar with. Gravity. Look, let me show you what I mean. Now, if I take a glass jar and fill it with some oil, add some water, leaving some room for the gas, or in this case, the air we breathe, screw the lid on tightly, shake it. This is roughly equivalent to the mixture flowing out of the wellhead. The three individual fluids are mixed together. Now watch carefully. Because of the different weights or densities of the three fluids, the force of gravity causes them to separate into three layers. The heaviest, water, sinks to the bottom of the jar. The gas, in our model air, being the lightest, rises to the top. Finally, the oil, heavier than air and lighter than water, collects in the middle. This is the basic principle in production separators. In reality, this process is affected by the temperature, pressure, and density of the fluid components. Now let's take a look at a typical production separator. The production separator essentially works like our glass jar model. But unlike the glass jar model, the production separator is designed to process a continuous flow of well fluids. On the job, you may hear separators called traps, knockouts, scrubbers, filters, and flash, or expansion chambers. These names are all applicable since they correctly describe various aspects of separators. So don't be surprised if you hear them. Whatever the name, this vessel is used to separate well stream liquids from gas components and debris. Now, the most recognizable feature of a separator is the large cylindrical tank. The well stream enters near the middle of the tank. On the uppermost part of the tank, gas exits through the gas outlet. On the top of the tank, you'll also see the safety devices built into the separator. A relief valve, and on some separators there's also a rupture disc, or safety head. The liquid level control valve, or dump valve, is located near the bottom of the tank. As the liquid level rises in the tank, the liquid level controller opens the liquid level control valve to maintain the proper liquid level within the tank. At the bottom of the vessel, a drain is available for cleaning out the solid debris which accumulates. Gauges and sight glasses on the vessel aid the operator in monitoring pressure and fluid levels within the separator. And that's the basics of a typical production separator. Some may be larger or smaller than the one we saw. And the vessel can be horizontal, vertical, spherical, but these basic features are relevant to all types. In addition, you'll hear separators called either two-phase or three-phase. Now, simply stated, a two-phase separator separates gas from liquids, and a three-phase separator separates gas, oil, and water. This is how it all fits together. A production separator separates free gases from the liquid stream at a specific pressure and temperature. For efficient and stable operation over a wide range of conditions, a gas-liquid separator includes a primary separation section, secondary separation section, liquid accumulation section, mist extraction section, along with control and safety devices. The primary separation section removes the bulk of the liquid in the inlet stream. First, slugs and large liquid particles are removed to minimize gas turbulence and re-entrainment of liquid particles. To do this, the velocity and direction of flow is changed. Centrifugal force created by either an inlet baffle or internal piping allows a change in flow direction and also a reduction of stream velocity. After stream velocity has been reduced, gravity pulls the larger liquid droplets from the gas in the secondary separation section. The efficiency of this section depends on the gas and liquid properties, particle size, and degree of turbulence. Some designs use straightening vanes here to reduce this turbulence. Before the gas leaves the vessel, the mist extraction section removes the very small droplets of liquid in a final separation step. The mist extractor can be a series of vanes, woven wire mesh pad, or a special chamber called a cyclonic passage. More recent designs use the woven wire mesh pad. Liquids are collected in the liquid accumulation section. By design, the liquid has minimum disturbance from the flowing gas stream. Two things determine the capacity here: the volume of well stream surges and the time the liquid must remain for efficient breakout of solution gas. That is, the gas dissolved or entrained in the well stream fluid. As the liquid level controller reacts to the accumulating liquid level, it triggers the liquid level control valve. The liquid is sent to storage or to further processing. Separators also have sight glasses for monitoring liquid levels. These devices allow the operator to check levels, check operation of the dump valves, and check for proper control functioning. Separators are equipped with several safety devices. These may include a Varick valve, relief valve, or rupture disc. They're all mounted near the top of the vessel. Well fluids enter the separator and may flow around the stationary deflector or baffle in the inlet. The fluids change velocity and direction when they come in contact with the baffles. The heavy fluids resist the change in direction, and the light fluids flow relatively easily in the new direction. Some of the liquids are forced against the sides of the separator, where they are caught in drains and channeled down to the bottom of the separator. Gas rises through the separator, carrying some liquid in the form of mist. This mixture passes through the mist extractor. This pad is usually made of knitted wire mesh. Liquid mist collects on the pad, and as droplets form and become larger, they fall into the liquid accumulation section. The gas leaves the separator through the gas outlet near the top of the vessel. Liquids and solids collect in the liquid accumulation section. Since this section is effectively isolated from the stream turbulence, gravity pulls on the heavy, dense solids such as sand and clay, settling them on the separator bottom. These solids are routinely removed during periodic maintenance. Liquids continue to collect until the level reaches the designed dump level. The liquid level controller opens the liquid level control valve, and the liquids flow from the separator into storage or to other process facilities. So far we've discussed the principles of fluid separation and how gravity causes wellhead fluids to break up into gas, liquids, and solids. Then we looked at a typical production separator with an inlet located near the middle, a gas outlet near the top, and a liquid outlet operated by level controllers near the bottom. We discussed the major components of a production separator: the primary separation section, secondary separation section, liquid accumulation section, mist extraction section, and control and safety devices. Finally, we followed the flow of gas and liquids through the separator. That pretty well sums up all the basics of typical production separators. But there are some other separator types I want you to look at.